Moving now to measures of central tendency. Here we will talk about the arithmetic mean or the arithmetic average. Then we'll discuss the median and the mode. We will also talk about other concepts of mean such as the weighted average, the harmonic mean, and the geometric mean. Before we talk about these different measures of central tendency though, let's understand the distinction between a population and a sample. A population refers to all members of a specific group. So for example, if a group is all the publicly traded stocks in the US, and let's say that there are 3,000 such publicly traded stocks, then this would be a population. A sample is a subset that is drawn from a population. So we might not want to study all 3,000 stocks. What we might want to do is take out a sample of 30. So this would be a sample. Any statistic that we create based on this sample would be called a sample statistic. So for example, if we calculate the average return over the last fiscal year for these 30 stocks, that would be called a sample statistic, and generally the sample mean is denoted by X bar. If we calculate the average for this entire population of 3,000, then that is called a parameter. So a parameter describes the characteristic of a population, and a sample statistic describes the characteristic of a sample. Now let's talk about the arithmetic mean. The arithmetic mean is basically the sum of the observation values divided by the number of observations. This is extremely familiar to most of us, so I won't spend too much time. We can calculate the arithmetic mean for the entire population, in which case it's generally denoted as mu. Here we will add the values for all the items and then divide by the number of items in the population. It's more common though to calculate a sample mean, which is denoted by X bar. Here we add up all the values and then divide by the number of values. So if we have these 9 values and we want to calculate the sample mean, we add them up. That will give us 72 and then divide by the number of values, that's 9. So our sample mean here is 8. The arithmetic mean or the average can be thought of as the center of gravity of the data set, and that's depicted over here. We have 2, which is shown here, and then 2 values of 4, so that's shown here, and then all the other numbers are shown. The average is 8. This is the arithmetic mean, and this essentially represents the number such that both the sides are balanced. So you can think of arithmetic mean as the center of gravity. If you understand this, that's great. If you don't understand this, not a problem. Just make sure you know this formula, that you calculate the mean by adding all the values and dividing by the number of values. From a testability perspective, it's important to recognize that the arithmetic mean is very sensitive to outliers. Outliers are extremely high or extremely low values. For example, let's say that to this data set we add another value of 89. So if 89 is added, that will move the arithmetic mean to the right. So the arithmetic mean will be very sensitive to an outlier. The question now is, how do we deal with outliers? And there are 3 broad options with respect to how we deal with outliers. One option is do nothing. And this will happen if we believe that the outliers are actually significant and we want to include them in the calculation of the mean. Another option is to delete all the outliers, and we will do this when we believe that the outliers are not adding value and we want to calculate a mean without the impact of the outliers. A 5% trimmed mean discards the lowest and highest 2.5%. So what does this mean? Let's say that we are evaluating a sample of 1,000 stocks, and what we want to do is consider the return associated with 95% of the stocks, and we want to ignore the top 2.5% and the bottom 2.5%. So what we'll do here is, let's say we take the numbers that cover 95% of the stocks. So let's say that in 95% of the stocks, our return is between -2% and +8%. So let's say this covers 95% of our data. Then we have the top 2.5% over here and the bottom 2.5% over here. With option 2, we will ignore these two. So we will ignore essentially the top 25 out of 1,000 and we will ignore the bottom 25. We will consider a sample of 950, which is in the middle. And the mean associated with this is called the trimmed mean. And given that we are ignoring 5% of the data, this is called the 5% trimmed mean. The third option is to replace outliers with another value, and this is called the Windsorized mean. The 95% Windsorized mean will set the bottom 2.5% of values equal to the value at or below which 2.5% of all values lie. So here, obviously, we have 25 returns that are less than -2%. All these returns will be set to -2%, and we have 25 stocks with a return greater than 8%. For these 25 stocks, we will set the return value to 8%. Then we will calculate the overall mean, and notice that in this case, we will consider 1,000 data points. It's just that we have removed the impact of numbers that are too high and numbers that are too low. Here is an excerpt from the curriculum that highlights how we deal with outliers. We have this equity index and we are looking at daily returns for the last 5 years. So we have this many trading days, 1,258. If we calculate the arithmetic mean, we get 0.035%, and we are considering all the observations. If we use a trimmed 5% mean, then we get a higher number. So this implies that we have returns that are very low, and now that those returns are being removed, the trimmed mean is higher. And also notice that the number of observations is lower because we are removing 5% of the observations. With a Windsorized mean, we go back to 1,258 observations, and here the mean is 0.038. So this is a little bit higher than the regular arithmetic mean. From mean, we move to the median. The median is the middle term of a set of items that have been sorted into ascending or descending order. So for example, if we have these numbers 2, 5, 7, 4, 11, they are already sorted in ascending orders. We have an odd number. So with an odd number, the middle term is fairly obvious. We have 2 on the left, 2 on the right. So that's an equal number of items. The middle number is the median. With an even number of items, the process is similar in the sense that we still need to sort the data in ascending or descending order. Here we have the data in ascending order, and in the middle now we have 2 terms. So 3 and 20 are on each side, 9 and 10 are in the middle. The median will be the average of these 2 numbers. So the median would be 9 plus 10 divided by 2, which is 9.5. An advantage of the median over the mean is that a median is not impacted by extreme values. So for example, if rather than 14, this was 40, the median would still be 7. On the other hand, the issue with the median is that it does not use all the information. So whether these numbers are 11 and 40 or 110 and 140, these numbers, and more specifically these high values, are not impacting the median. So this is a disadvantage in that all the information that we have in these numbers is not being used to calculate the median. The mode is the most frequently occurring value in a distribution. With this distribution, for example, the number 8 appears most frequently, therefore this is the mode. Sometimes data sets can have more than one mode. Here, for example, if we had 5 three times, then we would have two modes. So 5 would be a mode and 8 would be a mode. This would be called a bimodal distribution. And by extension, then, a trimodal distribution would be a distribution that has three modes. At times, we might have a data set which does not have any mode. So there can be several items, but each item appears only once. When we deal with continuous data, such as stock return data, where the returns are measured in several decimal places, then it's quite likely that we will not have two returns that are similar. In this case, especially working with continuous data, it makes more sense to use a modal interval. And here is an example. We have some daily return data, and what we have done is divided the data into different ranges. So from minus 4.1% to 3.3% and so on. Clearly, the modal interval is this one. So the modal interval represents the interval or the range where we have the highest frequency. In this range, from 0 to 0.9, we have the highest frequency of 493. So this would be called the modal interval. Now let's talk about some other concepts of mean, and specifically we look at the weighted mean or the weighted average, then we'll talk about the geometric mean, and then we'll discuss the harmonic mean. A weighted mean takes different observations and uses a different weightage or a different proportion for each observation. And this is understood through a simple example. Let's say we have this portfolio of 200 million where we have 40 million in stock A, 60 million in B, and 100 million in C. And then obviously there is a return associated with each of these stocks. If A returns 5%, B gives 7%, and C gives 9%, the question is, what is the overall portfolio return? Here, given that the amount invested in A, B, and C is different, it would not make sense to take the simple average of 5, 7, and 9. So here clearly the return is not going to be 7%. The return is going to be more heavily influenced by stock C because stock C has 100 million. So to calculate the weighted mean, we consider the weightage of each stock. With stock A, the weightage is 40 over 200. So we have 40 over 200 into 5% plus 60 over 200 into 7% plus 100 over 200 into 9%. And this gives a weighted average of 7.6%. In terms of a formula, we can say that the weighted average mean is equal to the sum of each weight. So let's say we have n stocks. So we have stock 1, 2, 3 all the way to n. So that's written as I equals 1 through n. We take the weightage of each and then we multiply each weightage by the specific return. So the weightage of stock 1 multiplied by the return for stock 1 plus the weightage of 2 times the return for 2 and so on. So this is the formula for the weighted mean. Now I want you to do this practice question. We have these different parts of a portfolio, local equities, international equities, and so on. And we are told that the relative allocation is this. We are also given the return numbers. You need to come up with the weighted mean. So hopefully this is what you did. The answer is 2.44%. Moving on to the geometric mean. The geometric mean is frequently used to average rates of change over time. So when we are looking at time series data and we want to calculate the average rate over a period of time or the average return over a period of time, then we use the geometric mean. The geometric mean is given by this formula. There is another formula, but that's less important. I will share that with you at the end. For now, I want you to focus on this formula. I will first use this formula and then show you very simply how it is derived. Let's say that the return over the last 4 periods for a stock is given by these numbers. We need to calculate the geometric mean. So the geometric mean is 1 plus the return in the first period. So 1 plus 10% would be 1.1 multiplied by 1 plus the return in the second period. So that would be 1 plus 8%, which would be 1.08. And then 1 plus minus 5%. So that would be 1 minus 0.05, which is 0.95. And then for 2%, it's 1 plus 0.02, which is 1.02. So we multiply all these numbers out and then raise to the power of 1 over the number of observations. The number of observations is 4. So we do raise to the power of 1 over 4 and then minus 1. When we do this calculation, we get 0.0358, which is 3.58%. So this is the average return over the last 4 periods, and we can say that this is the geometric mean. Now let me show you where this formula is coming from. We have 4 periods, so 1, 2, 3, 4. What we can say is that the geometric mean represents the average return over each of these periods. So let's say that the geometric mean is given by Rg. So if we have 1 plus Rg to the power of 4, this should be equal to this expression over here. So 1.1 into 1.08 into 0.95 into 1.02. This is because if we start with $1, at the end of the first period, that dollar will be this much. At the end of the second period, we will have 1.1 into 1.08 and so on. Therefore, at the end of 4 periods, we will have the product of these 4 numbers. Now, using simple algebra, we can see that 1 plus Rg is going to be equal to all this. So I will not rewrite it. Basically, this expression comes down and then raised to the power of 1 over 4. So we are removing this 4 and making this 1 over 4. And then this 1 comes over here. So basically, we have the product in the middle raised to the power of 1 over 4. In this case, n is 4 and then minus 1. So that's where this formula is coming from. And you notice, given this explanation, the last statement will make a lot of sense. The geometric mean, which in our case is 3.58%, represents the growth rate or the compound rate of growth on an investment. What we are saying is $1 over here grows to a certain amount based on these 4 returns. 3.58% is the average growth rate during these periods. So this represents the growth rate or the compound rate of return for our investment. Now, before you move on, I want you to pause here and make sure you memorize this formula. So given returns, you do 1 plus each return. If there is a minus return, then we have 1 minus that number. So this would be 1 minus 0.05, which is 95. We take this entire product raised to the power of 1 over n, and then we minus 1. Now I've given you this formula and I've shown you how to use this formula. But there is another formula that is less testable, but for completeness, I will share that with you anyway. Let's say you are given a bunch of PE ratios. So for a given stock, let's say the PE ratio has been 10, 15, 14, 13 over the last 4 years, and you are asked to calculate the geometric mean. The way you do this is you take the natural log, so the natural log of the geometric mean is equal to the sum of the natural logs of all these numbers. So I is equal to 1 through n. Here n is 4 divided by n. So in this case, what we are going to do is take the natural log of 10, add that to the natural log of 15, and so on. And then we will divide by n. And then to come up with the geometric mean, since this is ln over here, we are going to do e to the power of this expression. That will give us the geometric mean. Now, for completeness, you can do this, but the probability of being tested on this is low. If you do get a question on the geometric mean, you will almost certainly have to use this formula. It's important to understand when to use the geometric mean and when to use the arithmetic mean. The geometric mean is appropriate to measure past performance over multiple periods. So if we have time series data or return data over several periods and we want to calculate the average return per period, then it makes more sense to use the geometric mean rather than the arithmetic mean. And this point is illustrated through a very simple example. Let's say we have a portfolio where the returns over the last 2 years are 100% in year 1 and minus 50% in year 2. So let's say we start with $1. At the end of year 1, 100% return means that we end up with 2. And then in year 2, our return is minus 50%. So this means we come back to 1. So we can just see based on these numbers that our actual return over this period is 0%. And let's see what the geometric mean tells us. The geometric mean is basically 1 plus the return in the first period. So the return in the first period is 100%, which would be 1. So we would have 1 plus 1 multiplied by the return in the second period. So that actually is 1 plus minus 0.5. So that's going to be 1 minus 0.5. And then all this is raised to the power of 1 over 2. And then we have minus 1. So this gives us 2 multiplied by 0.5, which is 1. 1 raised to the power of half is 1. So essentially we have 1 over here. 1 minus 1 is 0. So this is telling us that the geometric mean is 0%, which is actually the return that we have over 2 periods. If we were to use the arithmetic mean, then we would take the average of 100 and minus 50. So that would be 100 minus 50 divided by 2. So this would be 50 over 2, which is 25%. So the arithmetic mean is 25%. And clearly we can see here that the more relevant number is 0%. So the bottom line is when we are looking at time series data or return data over a period of time, we should use the geometric mean and not the arithmetic mean. The next point has to do with the relationship between the geometric mean and the arithmetic mean. If we have data with no variability, then the geometric mean is equal to the arithmetic mean. So if we have two numbers and let's say we have 10% and 10%, then the arithmetic mean is going to be 10%, and when we calculate the geometric mean, that's also going to be 10%. So with no variability, the two are the same. But the more likely scenario is that we do have variability. So in this case, for example, we do have substantial variability. When there is variability, the geometric mean will be less than the arithmetic mean. And we saw that in our example here, the geometric mean was 0%, whereas the arithmetic mean was 25%. So remember the fact that in general, the geometric mean is going to be less than the arithmetic mean. And as the variability increases, so the numbers are very different from each other, then the difference between the geometric mean and the arithmetic mean also increases. So now the next question is, when do we use the arithmetic mean? The arithmetic mean is appropriate for forecasting single period returns. It's also appropriate when we are looking at cross-sectional data. So for example, if we have stock X and in the next period, the return could either be, let's say, 30% or 20%. So these are the two possible returns. There's a 50-50% chance of each. We can say that the expected return is 25%. So this is one scenario. Another situation is that we have two stocks in a portfolio, stock A and B. The expected return on A is 30%. The expected return on B is 20%. So the expected return on the portfolio, assuming equal weightage of A and B, would be the arithmetic mean of these two, which is 25%. The final type of mean that we will discuss in this segment is the harmonic mean. The harmonic mean is a special type of weighted mean in which an observation's weight is inversely proportional to its magnitude. And it's this inverse relationship that's reflected in the formula. I will come to this formula shortly. The harmonic mean is appropriate for averaging ratios when ratios are repeatedly applied to a fixed quantity to yield a variable number of units. A classic example here is cost averaging. Say an investor wants to spend $1,000 every month, so this is a fixed amount of money, to buy a particular stock. Now obviously every month the stock price or the share price will be different. So let's say in month 1 the share price is 10, in month 2 it's 15, month 3 it's 20. So the amount of money being invested is the same, but the share price is different. And we want to know what is the average purchase price. And this is where we use the harmonic mean. So to calculate the harmonic mean, we add the reciprocals of these three numbers. And these reciprocals are going to be in the denominator. So we will have 1 over 10 plus 1 over 15 plus 1 over 20. And then the number of observations, which is 3, will go in the numerator. When we do this calculation, we get 13.85. So this means that the average purchase price was 13.85, and this is the harmonic mean. So now again, I want you to memorize this formula. We have the number of observations in the numerator, and then in the denominator, we have the sum of the reciprocals. Well, I do want you to learn this formula, but I also want to show you a more intuitive way of doing this. And this method will illustrate why we are not using 1000 as part of our calculation. So we can say that the average purchase price is the total amount of money spent divided by the number of shares purchased. Since he's spending $1,000 per month for 3 months, the total amount of money spent is 1000 into 3. That's the total amount of money spent. The number of shares purchased is equal to the number of shares purchased in the first month, which would be 1000 divided by 10, plus the number of shares purchased in the second month, that would be 1000 over 15, plus the number of shares purchased in the third month, that's 1000 over 20. Now notice over here, using simple algebra, the thousands would cancel out and we simply have 1, 1, 1 over here. So effectively, we are left with this formula. We have 3 in the numerator, which represents the number of items. And then we have the reciprocal for each item in the denominator. And this obviously will give us the same answer of 13.85. But again, even though I want you to understand this intuitive explanation, it is important for you to memorize this formula. The number of items in the numerator and then the sum of the reciprocals in the denominator. Now let's talk about the relationship between these three means, the harmonic mean, the geometric mean, and the arithmetic mean. As I said before, if there is no variability, the geometric mean is equal to the arithmetic mean, and we can throw the harmonic mean into this mix also, as long as there's no variability. So for example, if we have three numbers, 10, 10, and 10, the arithmetic mean will be 10, the geometric mean will be 10, and when we calculate the harmonic mean using this method, we will also get 10. But in the real world, there is variability, and when we do have variability, then the harmonic mean will be the lowest So we'll have the harmonic mean being less than the geometric mean, being less than the arithmetic mean. And as the level of variability increases, the difference between these three means also increases. Now, the curriculum in passing just mentions that the relationship between these three is more specific in that the harmonic mean times the arithmetic mean is equal to the geometric mean. I think this is just given as a point of interest. I don't think that you are likely to be tested on this particular relationship. What is much more important, though, is for you to understand which mean to use in what circumstances. The arithmetic mean should be used with single period data or with cross-sectional data. So if, for example, we have stock A and B in equal quantities or in equal dollar amounts, A has a return of 10%, B has a return of 15%. You are asked what's the average return, you should calculate the arithmetic mean. Or if stock A might have a return of 10% or 20% in the upcoming period, what's the expected value? The answer is that you use the arithmetic mean. The geometric mean is used for time series data. So let's say we have return numbers over the last 4 periods and we want to calculate the average return per period. We will use the geometric mean. The weighted mean is used when we want to allocate a different weightage to different numbers. So in a portfolio, we might have 3 stocks A, B, and C, and the amount invested in these 3 stocks is different. We want to come up with the overall return for the portfolio. We should use a weighted average. Clearly, the stock that has more money invested in it should get a heavier weight. With harmonic mean, the classic application is with cost averaging. This is where we are using the same amount of money to buy a stock every period, and we want to calculate our average purchase price. A trimmed mean is used to deal with outliers. So with a 5% trimmed mean, we use 95% of the values in the middle and we ignore the top 2.5% and the bottom 2.5%. Winsorized mean is also a technique for dealing with outliers, but here rather than ignoring the bottom 2.5% and the top 2.5%, we take the bottom 2.5 and assign them the value from here, and we take the top 2.5 and assign the value from here. So the number of observations remains intact, but we are reducing the impact of extremely high and extremely low values. So that is it for this segment.